Okay, welcome to today's notes on parallel circuits. The first few videos that we did, we were really focusing on series circuits. Today, we're going to learn about a different type of circuit. This is fundamentally different from what we've done so far, but you'll see that there are also rules for these, and the rules are not all that bad. Series circuits were defined because they only have one path for the current to flow through. There's only one place or one route for the current to go from one terminal of the battery to the next. On the other hand, parallel circuits have multiple paths for current to flow through. So you can see them drawn in a number of different ways. I'm going to draw a couple different ways right here. This is how I learned how to draw them. Nothing necessarily wrong or right with this way. It's just one way people do it. Notice that I have right here a junction in the circuit where current could either go up through this resistor or down through this resistor. Then I have another junction where the current recombines and it flows back to the resistor. Okay, so current could either take the upper path or this lower path here. Current cannot go through this resistor and then flow back through this other resistor because it would be going against the charges that are flowing this way. Current, you're never going to have two currents that are flowing in the same wire in opposite directions. Current always flows in one direction. Okay, it's like a rock rolling down a hill. It's not going to suddenly turn around and go back up the hill. It's just going to keep rolling down. The other way that you could draw circuits that I've seen, parallel circuits that I've seen done, right now we just have a series circuit, but look, we're going to put a junction in, and now this is a parallel circuit. Matter of fact, I could even put another junction in. You can have a 3-branch parallel circuit. So 3 different resistors, 3 different paths for the current to take. Parallel circuits with resistor in them still follow Ohm's law. Remember, Ohm's law is this, V equals IR, but they have different rules than series circuits. There's different implications. The rules for series and parallel circuits are different. So what you have to do is you have to get good at analyzing and seeing right away, is this a series circuit, is this a parallel circuit? And before I forget, I just wanted to show you these two types of circuits on our simulation here on FET circuits. So we can see that the current is splitting. This is the first type that I drew. Okay, I shouldn't say type, but the first way that you can draw a parallel circuit, you can see that the current is splitting here, recombining here. And the second one, you can see that the current splits here, and it also splits here, and then recombines here and here. Just 2 different ways to draw parallel circuits. Okay, they show the exact same thing. The key is that there are junctions where the current either splits or recombines. All right, rule number 1 for parallel circuits. For a very simple parallel circuit with 1 resistor per branch, we're going to focus on this. Circuits with 1 resistor per branch. By branch, we mean the multiple paths that it can take. The voltage drop for each resistor is the same. I'm going to do 2 things. I'm going to draw you the same circuit twice, and I'm going to show you how to correctly analyze it and how you would not correctly, or like the incorrect way. We're going to start with the incorrect version so that you can avoid it. The incorrect version of analyzing a parallel circuit would be to do this. Let's say you have a 6-volt battery connected in parallel to 2 resistors. And you have a voltmeter, that's a symbol for voltmeter, going across both resistors. So notice that the voltmeter has probes before the current gets to the resistor and after the current gets to resistors, so it should be measuring the voltage drop for that resistor. Now, the wrong way to do this is to say, okay, well, my voltmeter would read that this has a voltage drop of 4 volts and this has a voltage drop of 2 volts. 4 plus 2 is 6. Everything's good. That would totally work if this was a series circuit. If this was a series circuit, absolutely. But this is a parallel circuit, and that doesn't make sense. Here, what the person has done is they've taken the voltage drops and they've made it so that they add to 6 volts. But when you think about it, this would not work because the charges would have contradictory energies. Here's what I mean by that. Remember that voltage drop just tells us how much energy is given off per amount of charge. If you have charges flowing around this circuit, then let's say a charge goes through the 4 volt, or this resistor, where it loses 4 volts. Okay, that's how much energy it gives off. Another charge that goes through this branch would lose 2 volts. Okay, so that's how much energy would give off per charge. When they recombine, you would have 2 charges once they recombine, that would be a situation where you have 2 different charges with 2 different amounts of energy here. That's not how this works. That would be like if you and a friend took different paths, you were at the top of a mountain, you took different paths down the mountain, got back to the same spot, and you said that you lost, 1,000 feet of elevation. Your friend says they lost 2,000 feet of elevation. It doesn't make sense. You started in the same spot, you ended in the same spot. The amount of elevation change would have to be the same. This is the same idea here. If the potential difference between the terminals of the battery is 6 volts, that means that 6 volts needs to be lost by the charges as it goes through the circuit. You can't have a charge that has lost 4 volts here and another charge that's lost 2 volts. That doesn't make sense, okay? It's conflicting, all right? And plus, when they get back to the battery, that would show that there is not a 6 volt difference between the terminals of the battery. It would show it's either 4 or 2, neither of which makes sense. Here's what really happens. Here's the correct version. You have a 6 volt battery. You have your 2 resistors. And you have your voltmeter to measure. The voltmeter, no matter which one you attach it across, would read that both of these have voltage drops of 6 volts. So what we're seeing here, the rule when we were talking about series circuits was that the total voltage drop of the circuit was equal to the voltage gain of the battery. And that's true for series circuits. For parallel circuits, the rule is the voltage drop for any complete loop of circuit must be equal to the voltage gain of the battery. Matter of fact, that's true for all circuits. It's just that with series circuits, there's only one loop to go around. So here, you have 2 possibilities for your loop. You could start at the battery, go through this left-hand resistor, and back to the battery. You could start at the battery, go through this right-hand resistor. Both of those are separate loops. The voltage drop for the entire loop must be equal to the voltage gain for the battery. That is the rule. So I'm just going to write here, each drop is equal to the total voltage. I'm going to show you this on the simulation very quickly. We have a 6 volt battery, and I have 2 resistors. One has a resistance of 1.8 ohms, the other has a resistance of 9 ohms, so they don't even have the same resistance. Notice that we said nothing about the resistance down there. They don't even have the same resistance, but if I look at the voltage drop for either one, that's 6 volts, and that's 6 volts. Okay, the voltage drops are the same, and they're equal to the voltage gain of the battery, which, as it told us, is 6 volts. Okay, so we see that the voltages are different. As a matter of fact, I'm going to give you the equation that governs this. For a parallel circuit, right here, the voltage from the battery is equal to voltage drop for 1 equals a voltage drop for 2 equals a voltage drop for 3, etc., etc. So we're just going to write that in right here. Vt equals, V1, which is equal to V2, which is equal to V3, ... Now, this is true for simple parallel circuits, the ones that we will analyze in class. If you start to mix up series and parallel circuits, like you have some series parts and some parallel parts, this is not necessarily going to be true. But for our purposes, for very simple parallel circuits, it is. Second point, each branch of a parallel circuit can have a different current, a different amount of current in it. The sum of the currents in each branch of the circuit is equal to the total current flowing out of the battery. And the higher the resistance in a branch, the lower the current in that branch. Again, I'm going to show you the incorrect way to look at this and the correct way to look at this. The incorrect way to look at this, I'm going to draw the same basic setup. Remember how we put ammeters in? They just kind of go right, they get wired right into the circuit. You don't put them around anything. So what we have here is a circuit in which we're measuring the total current flowing out of the battery. Let's say that that was 4 amps. The incorrect way to analyze this would be for a person to say, oh, if the current up here is 4 amps, then the current down here must be 4 amps, and the current down here must be 4 amps. Okay? That's perfect series circuit logic. That's perfect series circuit logic. It does not work for parallel circuits, and here's why. The current out of the battery is equal to 4 amps, and the total current in the branches equals 4 amps plus 4 amps, because here's branch 1, here's branch 2, 8 amps. Now what does that mean? Remember what current is. It's the number of charges that pass by a certain point in a certain amount of time. How could the total current be 4 amps, but then suddenly in the branches there's now 8 amps of current? Where did all that extra charge come from? It doesn't make any sense. There's something called conservation of charge. Charges don't just magically appear out of nowhere. You can't have 8 amps of charge flowing here, but only 4 amps up here for the total. It just doesn't make sense. There's a rule called conservation of charge. So how did current just magically increase? It would never do that. Here's the correct way. And it leads into number 3. The correct way to analyze this would be, here's our ammeter here. My resistor drawing is getting pretty bad. Would be if this is 4 amps up here, then these can be any combination that add up to 4 amps. Okay? The current in the sum of the currents in each branch of the circuit is equal to the total current. So this could be 3 amps, this could be 1 amp, it could be 2 and 2, it could be 3.5 and 1.5, whatever, as long as the branch currents add up to 4 amps. Here is where the current splits. Some of the current goes this way, some of the current goes this way, but added together, they still equal the total that was coming out of the battery. Here's where it recombines, and we get the total current all together again. So this is correct because the branch currents, if I could spell, that would be great. Branch currents add to equal the total current out of the battery. Okay, and this kind of ties into number 3, the amount of current flowing into a junction, a meeting of wires, a meeting of wires, must equal the current flowing out of a junction. This is just a restatement of what is known as the law of conservation of charge. We've talked about that before. When we were drawing pictures of objects getting charged, I told you that you can't just randomly, once you draw how many charges there are, you can't just randomly start adding more charges unless a new object comes in or unless you ground the object. You have to keep a consistent number of charges. So let me just demonstrate this for you real quick. You sometimes see these questions. Let's say that you have a junction right here, and you have some wires coming into and out of this junction. Let's say that you have 6 amps flowing in this way, and you have 5 amps flowing in this way. You have 7 amps flowing out this way. How much current is flowing out in this direction? It's not really an equation, but you can still write it if you want. We have current in must equal current out because of law of conservation of charge. 6 amps plus 5 amps are flowing in. 7 amps plus X is flowing out. X must therefore be, since 6 plus 5 is 11, minus 7, X must be 4 amps. There we go. Oh, and I should say, since each branch of this parallel circuit can have a different current in it, I do just want to show you that equation really quick. It is right here. I equals I1 plus I2 plus I3 plus dot, dot, dot. I total equals I1 plus I2 plus I3 plus dot, dot, dot. Let me demonstrate this for you real quick on here. If the current is 4 amps as it comes out of the battery, then we expect the current in the branches to add together to equal 4. 3.33 plus 0.67, I'll leave it up to you to double check that's 4. That's not each 4, but the sum is equal to 4. And let's go and take a look at another example. I've got to kind of zoom in for this one. This is what we just did. If the sum of the current going in, you can see that the current going in is 5 amps plus 6 amps, going out is 7 amps, and then also going out is 4 amps. Total of 11 in, total of 11 out. Last thing I want to talk about is the equivalent resistance formula. For series circuits, this was very basic. It was just add up all the resistors. It is not as easy for parallel circuits. It's not hard, but you do have to be a little careful with your math. The equation is 1 over the equivalent resistance for parallel circuits equals 1 over R1 plus 1 over R2 plus 1 over R3 plus ... So, yes, you do have to write this equation each time. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3 plus as many times as you need. Couple things to notice. Even though we have fractions here, as you keep adding resistors in, you're going to keep increasing this side, which means you're increasing the inverse. But what happens when you take the inverse? Okay, if you're increasing something and then you take the inverse of it, that means divide it by 1. Think about what happens when you keep, as the bottom of a fraction gets bigger and bigger, and then you add, or excuse me, if this number on the right hand side keeps getting bigger and bigger, then you take the inverse, you're going to end up with something smaller. Okay, think about like a fraction. If you just keep adding like 1/3 plus 1/3 plus 1/3 plus 1/3, the right hand side is going to be getting bigger. Once you take the inverse, you're going to get a smaller number. So, what I'm trying to demonstrate here is Req is always smaller than the smallest resistor. And you'll see that as we do these problems. And if you keep adding branches in parallel circuits, as you add branches, as you add resistors in different branches, that means you have less Req. And if you think about Ohm's law, if the resistance goes down but the voltage stays the same, that leads to more current. You can think of this as you're basically adding more space for the charges to flow, so the current will be higher. It's less congested. Let's get to some examples. Our first example is just figuring out the Req of a couple different situations. What is the equivalent resistance of the partial circuits shown below? Now, there's a couple different ways you can do these. I would say for this, let's write our equation. Req equals R1 plus R2. I'm going to plug in my numbers. 1 over 25 ohms plus 1 over 45 ohms. I'm going to figure out each of those separately. 1 divided by 25 is 0.04. You can write that down if you wish. And then you need to add 1 over 45 to that. So on my calculator, here's what I'm going to do. I'm going to do plus parentheses 1 divided by 45 and parentheses. That's what 1 over 45 is. I hit equals, and that's going to add it to what I had before. 0.0622222222. That is equal to 1 over the equivalent resistance. In order to get the equivalent resistance, I have to divide this. I have to take 1 and divide it by this number. I need to take the inverse. My calculator has a fancy button to let me do this. 1 divided by x. Your calculator might have x raised to the -1. Either of those buttons, if you press it, will give you the inverse. Notice that the Req is less than either of the resistors, 16.07. And I will just go back and show, if I do 1 divided by 0.062222, I get the same thing. Same deal over here. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. 1 over 600 ohms plus 1 over 700 ohms plus 1 over 800 ohms. One divided by 600 plus parentheses 1 divided by 700 and parentheses plus 1 divided by 800 and parentheses equals, take the inverse, 230.14 ohms. Now, for an entire circuit, you know the total voltage drop, the total current, and the resistance of one resistor in the parallel circuit below. We're going to find the equivalent resistance, the resistance of this resistor, the voltage drops for each resistor, and the currents through each resistor. The voltage drops are easy because remember, one of the rules in a parallel circuit is that all voltage drops in a parallel circuit are equal to the voltage gain of the battery. So that means that this is 9 volts. This is also a voltage drop of 9 volts. Got that one done. Okay. A bunch of different ways I could do this now. Let's find the current through this resistor. Ohm's law applies to any part of a circuit. The voltage drop is 9 volts. The current is unknown. I'm going to call this resistor 1, and the resistor is 150 ohms. I equals 9 divided by 150. The current is 0.06 amps. Okay, 0.06 amps. And since the total current in a parallel circuit is equal to the sum of the current in the branches, that means that since the total current is 0.18 amps, the total current, or the current in branch 1 is 0.06 amps, we can figure out the current in I2. That should be 0.12 amps. Okay, so there's the currents through each resistor. Now that we have the voltage drop and the current, I could find the resistance. 9 volt drop, current of 0.12 amps times R2. $75 ohms. And I can double check now that I know almost everything, the equivalent resistance a couple different ways. I could either do the total voltage equals the total current, the voltage gain of the battery, I should say, times Req, where I have 9 volts equals, let's see, 0.18 amps, Req, 9 divided by 0.18, Req is 50 ohms. I'm going to double check that by doing this. 1 over Req equals 1 over R1 plus 1 over R2. And sometimes you don't even really have to do all the math for this. This will be 1 over 150 ohms plus 1 over 75 ohms. If I need to get common denominators here, I multiply this by 2 over 2. I get 2 over 150, which would give me 3 over 150 when I add these together. If I take the inverse of 3 over 150, I get 150 divided by 3, which is 50. Req equals 50 ohms. You don't have to double check, but it is nice to know that everything worked out. So what I'm going to show real quick is all the examples that I've done so far, or at least everything except this one because I can't get those resistances. 25 ohms, 45 ohms. The equivalent resistance should be about 16. I can get the equivalent resistance by doing the battery voltage of 32 divided by the current of 1.99, and we get 16.08. The equivalent resistance was 16.7 last time. That checks out. All right, here's the big example that we did. Let's see here. I know the total current is 0.18. I've set this up so that the battery voltage is, where's my other probe? There it is. 9. If I look at the voltage drops across the resistors, those are also 9. I just have this middle part is just two 75 ohm resistors since it should be 150 ohms. And here I'll just check values for that. 75 and 75 just got them smushed together, so that's 150. And the currents, 0.12 in that branch, 0.06 in that branch. So notice that the current is bigger in the branch with more resistance, or excuse me, the current is bigger in the branch with less resistance than the branch with more resistance. Okay, just like we found. And then last but not least, we already did one problem like this, but I'll do another one. What's the reading on the ammeter in the partial circuit shown below? Well, we know the current in must equal the current out. 5 amps plus 3 amps equals 7 amps plus X. 5 plus 3 is 8, minus 7 is 1. 1 amp must be what X is equal to. And I've even got an example of this set up here. If we zoom way in. 5 amps flows in, 3 amps flows in, 7 amps goes out, and 1 amp goes out in that bottom right-hand side. Just like with series circuits, parallel circuits have a set of rules to them. The rules are fairly straightforward. Your job is to recognize whether we're talking about a series circuit or a parallel circuit. Usually it tells you, or the diagram is drawn for you. And once you do that, to apply the rules correctly. The rules are all listed right on your reference tables. It tells you this current in a series circuit is the same everywhere. It tells you that the voltage drops sum up to the voltage of the battery, and it tells you the equivalent resistance. Same for parallel, except the rules are reversed. Or not reversed, I should say, but the rules are different. In a parallel circuit, the sum of the branch currents equals the total current. All the voltage drops are the same as the voltage drop of the battery, and the equivalent resistance is different. Now it's up to you to practice understanding and analyzing both of those types of circuits. See you later.